those two designs, this is what a possible four-panel design would look like. We'd have two extra sails on the top, and that would allow for rotation not only about the z-axis, but it would help rotation along the y-axis as well. And now heading off to Dennis to talk about the electrical design details.
Thank you. Hello everybody, my name is Dennis. I'm doing the electrical design details. Here we have a diagram of the attitude control, the way the attitude control system is going to be wired. We have the paddles on the side coming out of our Cubesat in the middle. And for visualization purposes, we put the servo motors on the outside of the Cubesat. In reality, they actually be on the inside of the Cubesat. And these servo motors are connected to an Arduino, which will then be connected to our laptop for provide power. This is just our test setup. In our actual flight model, we'll have the Arduino actually housed inside of our Cubesat, connected to an onboard power source. Here we take a closer look at our servo motors. They're actually micro servo motors. They weigh about 9 grams each. They're very small. It's very difficult to send something to space with a lot of mass and size, so we're very conscious of keeping everything as small as possible. These servo motors also have a rotation angle of about 180 degrees, which might seem like not a lot, but it's actually more than enough since we're rotating a maximum of 90 degrees. Here we conducted a small trace setting between the FST6 RC controller and the Arduino main. With the RC controller, it comes with these small receivers that we're able to connect our servo motors to. This is actually very helpful for us because it reduces the need for wiring, and it will also give us full control of our servo motors right at our fingers on this RC controller. Now the downside to this RC controller is that we can't program it using MATLAB or Simulink or any other type of program like that. Which, since we can't program it, we're not able to automate it. Since we can't automate it, we won't be able to use this method on our flight model. And now the Arduino Mini, we actually do need to do a bit of wiring, and we do need to do a bit of programming. But once we do that, we have full control of our servo motors. And since we are able to program it, we'll be able to automate this process. And due to this information, we'll be using the RC controller for our testing inside of our lab, and our Arduino Mini for our presentations in our lab. Here we take a closer look at our Arduino. As you can see from the specs, it has a variety of input and output pins, which will be helpful for us because not only do we have the servo motors that make our paddles to worry about, but we actually have to worry about other electrical components inside of our Cubesat that need to be controlled as well. And with our Arduino, it's very small, so it actually helps us keep the size and weight down for our flight model. Here we have a simple circuit that we're able to control a servo motor using a potentiometer. This is interesting because we can actually swap that potentiometer out for a type of sensor, and with that sensor, we're able to actually automate this whole process and have the Cubesat keep its own orientation while up in space. Here we have a Simulink model that actually calculates the angular position, angular acceleration, and angular velocity of our Cubesat. Now in this model, we have our paddles configured to one being perfectly perpendicular to the solar wind and the other being perfectly parallel to the solar wind. Now this configuration actually produces the maximum amount of torque, which will give us then the maximum amount of angular acceleration. On this side we have 3 graphs: angular position, angular velocity, and angular acceleration. Now in each of these graphs we have 2 curves. The yellow curve represents our mechanical actuation method, and this blue curve represents our reflectivity chain, the reflectivity chain method that other spacecraft might use. As you can see, our mechanical actuation method actually yields much greater angular acceleration than the reflectivity chain, which will then give us a much higher angular velocity over time, which then will be able to change our angular position much faster. And with that, I'd like to hand it back over to you.
So I'm back with risk assessments, and I'll go over technical and the schedule risk. We're mainly concerned about medium, high, and high, which is fan failure, which has happened already, but we're able to fix that. And then we also have sensor failure, communication failure, and hardware software interface issues. Our mitigation approaches would be breadboard testing and frequent simulation testing. And on our next slide, I'll go over the schedule risk. Our wind tunnel, these are medium. Wind tunnel is done. We might have to make a few modifications on velocities or anything else. And as far as change in requirements and project scope, highly unlikely, but hopefully it doesn't happen, because it would be give us serious consequences for our project. And as far as overview of our risk, as we've been able to manage to stay away from the severe area. Most of them are unlikely when possible. So our project is, as far as risk, is looking pretty good. And next, I'll give it to Apollo for our summary.
Thank you, Espoir. Overall, our project prognosis is looking pretty good. We are on schedule with everything, and we have no foreseeable cost-related risks. Also, our simulation outputted results that were consistent with our hypothesis, which is always a good sign. In summary, our achievements this summer include creating a Simulink graphical user interface where we can enter angles and solar sail size and also distance from the sun, and it'll give us angular response plots. And from those plots, we found that mechanical actuation is more effective at producing attitude control than the alternative. In fact, when we compare our simulation numbers to a real-life example of solar sail attitude control, which is Icaros, we see that our numbers compare quite favorably. Icaros was able to achieve a degree of change per day, but we project that we can achieve a degree per half hour. Our testbed team has finished with the miniaturized laminar wind tunnel, and right now we're working on making sure that the test articles being put in the wind tunnel give us optimal results for what we want to see. And our objective next semester is to outfit this with an autonomous closed-loop feedback control. So folks, what we presented to you today is not so much solar sailing as it is, and we're going to invent a new term here, so get ready, solar steering. And when you combine this technology with the mobility of small spacecraft and CubeSats, well, the possibilities are endless, both for our planet and beyond, wherever Kepler's heavenly breezes take us. Thank you all so much for listening, and let's take some questions.